Alright, let's move on. So we're going to discuss a different mechanism for the carriers to move in the semiconductor. This is called the diffusion. This is different from the drift. Drift is where we have the electric field, but the diffusion does not depend on the electric field. The diffusion happens when you have different concentration of your carrier. For example, here you have higher concentration of the electrons in this region to the left, and then you have lower concentration of electron in this region to the right. So you know those electrons, like particles, tend to diffuse out from high concentration region to the low concentration region. So this will happen naturally, and then this is called the diffusion. So in this case, electrons move to the right, then your electrical current by diffusion will be the left. So this is the diffusion, and we can actually quantify the diffusion current using the gradient of the concentration. So if you think about the N, the electron density is non-uniform along the x direction in this semiconductor. If we have this kind of profile, then we can define the slope is dn over dx. So if you have steeper slope, then you know the diffusion will be faster, right? You have more difference between those two regions, then the electrons tend to diffuse faster. So the diffusion current then is proportional to this slope, dn over dx, and then we define this coefficient as the diffusion constant. And of course, you need to carry the charge quantity Q here. So this is for the electron, and as you can see here in this example, the electron, you have higher electron density here, so you have more electrons here and less electron here. So electrons tend to move to the left, and then by definition, currents will move to the right. And then similarly, we can look at the hole diffusion. Again, we have similar profile. Then the hole, you have more holes here, less holes here. Then hole tend to move to the left, and the current will be the same direction to the left. So here you need to have the negative sign, because to the left means negative direction. So here the same formula, but the only thing is the sign is different. This is because of different definition of the electron and hole. But again, this depends on the slope. Any questions? All right, so if you consider all the components of the system, the total current density can be contributed by either electron current density or the hole current density. So it's a sum of those two. And for the electron density, you can consider two mechanisms. One is drift. This is under the electric field. And the other one is the diffusion. This is when you have the slope of the electron density, dn over dx. That is the slope. So you see the current has those two kinds of mechanisms. And similarly for the hole, you can divide that into two: drift and diffusion. And then here the only difference is this negative sign, as we see in the previous slide. So here this is the total current in the system. And of course, if you talk about N-type semiconductor, then electron dominates. So you only need to take care of this Jn. So the J total is almost the same as the Jn in the N-type semiconductor, because hole is a minority. You can ignore that. And for the P-type, you can only consider the hole current density. Only when you are in the intrinsic semiconductor where the electron and hole are comparable, then you may need to consider both. Alright, then before we talk about this one, any questions? Okay, so let's talk about the drift under the external electric field. So here, think about this N-type silicon, and we apply voltage across that. So apply positive voltage to the left, and then we ground the right. And in this case, you will have voltage drop from the 0.7 volts to 0 from the left, if we think this is 0, and then here is the x. So we want to look at the band diagram under the external electric field. And here we will, this is very important. When you apply the electric field to the silicon, you are going to bend the band. If you recall previously, in the lecture 5, we talk about the band diagram. You have the EC and your EF and your EV. And this is N-type, so you know the EF is close to the EC. My pen doesn't work. This is close this. Still doesn't work. That's not good. Try one more time. Okay. Okay, so here, without electric field, then the energy band is flat. But with the electric field, the conclusion is that the positive voltage will push down the band. This is because the band is respect to the electron's energy, and the positive voltage will lower the energy for electron. And here, if we apply 0.7 volts, this band actually will be pushed down by 0.7 electron volts. So this is a very important conclusion. Positive voltage to the left is going to push down the band from the left. And the second conclusion here is that the EC, EF, EV will be parallel to each other. So when you push down the EC, you are going to push down the EF and EV by the same amount. So eventually you will have this kind of parallel EC and EF and EV. And then we want to argue that the slope of this band is actually the electric field. So why is that? The electric field is, by definition, the voltage derivative respect to the distance. The voltage divided by dV divided by the distance dx. And then you take the negative sign here, by definition. And then the voltage and the energy EC. The relationship is, the electron's energy is the charge times the voltage of that electron. So then here you can replace the dV as a dEc over Q. So this dEc over dx, what is that? That is the slope in the band diagram. Slope in the EC. And we said that this is in parallel with EV, so it will be the same slope in EV. So this is an important conclusion. If you have any bented, let's say any tilted or bent band edge, that means you have electric field in the system. And here, the electrons in the conduction band, you have electric field to the right, electrons will move to the left. And here another conclusion is that the electrons will always try to fall down along the band edge to the lower potential. The electrons, like the water. This is an analogy we are going to use over and over in this semester. Electrons, like water, tend to go to lower potential in the energy band, so it will fall down to the left. Meanwhile, if you have a hole in the valence band, then the hole will move along the electric field, will move to the right, and then hole will move up along the band edge EV. So then we can also use an analogy for the hole. And what is that? Can you guess? Hole is like what? Any idea? Anyone want to volunteer on the chat? We say that electron is like water. Electron is like water, go to the lower potential. Then hole is like what? Go to higher potential. Hole positive. Yeah, hole is positive, but this is not an energy we want to draw here. Gas, people, air. Oh, I got many answers, interesting answers. But let's make it similar as the water. So if you think about water, go to lower potential, and then something in water will move up. What's that? Ice? No. So if you take out, you think about electron is water, right? If you take some water out from the system, then what is left behind? It's like the hole is the vacancy of the electron. Then what is the vacancy of the water? Bubble, yes, I got it. Yes, you are right. Bubble. Right? So bubble tend to move up in the water, right? So this is like hole. So hole tend to move up and the electron tend to move down. So this is a very important conclusion we want to draw. Okay, later when we talk about the MOSFET, the transistor operations, we will also use those analogies. Okay, all right. So this is what we want to discuss on this slide. And then let's look at another example here. This is an N-type semiconductor, but with non-uniformly doping. So here, let's assume you have more doping to the left. So you have more electrons here. And then you have less doping to the right. So the donor concentration will decrease to the right. So you have more electrons to the left, less electrons to the right. And let's consider this example. And we consider it without external electric field. This is another assumption we want to make in this example. There's no external electric field. Okay. First of all, we have the non-uniform doping, and you have more electrons to the left, less electrons to the right. So what we just discussed, there will be diffusion, right? So the diffusion will make the electron move from the left to the right. And then we can consider this band diagram. So the left, you have the larger ND, right? Let's say the ND, let's say this is 0, and this is your X. And this ND0 is larger than the NDX. So you have more doping here. If you recall the last lecture, we talked about that the higher N-type doping, the EF is closer to the band edge EC. So the distance here is determined by the doping density, and you have done the homework. So you know you can calculate this based on the doping density. And the higher N-type doping, closer EF to the EC. Then to the right side, you have less doping, so then this is farther away. Then you have larger distance here. And we want to draw use another, let's say, truth here. That is always true. If the system is without electrical field, we call it in the equilibrium state. Equilibrium state. Equilibrium state. In equilibrium state, EF is always flat. The Fermi level is flat in the equilibrium state, or the Fermi level is flat when you have low electric field applied externally. If you don't apply voltage, the system is in the equilibrium state, and EF is flat. So EF is flat, but you have different distance to the EC. That means EC will have this slope. EC is bent. So EC is bent. We just have the conclusion from the previous slide. You see here, if the band edge is bent with a slope, that means what? You have electric field, right? So you have electric field. This is a built-in electric field. This is not what you applied, because externally you apply 0 voltage. You don't have the field outside. But this is built-in electric field. Because of the slope. So if you have built-in electric field, that means what? If you consider the drift current, then the electron, will move to the left, because the field is pointing to the right. In the same example here, the field is pointing to the right. So electron, like water, will go to lower potential. Electron will go to the left. So electron will go to the left. This is caused by this drift. But externally, you don't have voltage. Then the net current should be 0. That's why here you have two internal currents. The diffusion current is towards the right, and the drift current is towards the left. and the diffusion and the drift should cancel each other because the net current should be 0. Externally, you don't apply voltage, then there's no net current. So this is what happened internally to the semiconductor here. Because of the non-uniform doping, you have both diffusion and built-in potential, and then those two cancel each other. Any question? All right. So then we can derive the relationship between the drift and diffusion using this example. So in other words, there's a relationship between the diffusion constant d and the mobility mu. So let's do this, okay? So let's have some derivation. The electron density n equals to nc exponential this EC minus EF over KT. This is what you have learned from the last lecture. And in this example, the n is non-uniform, okay? Because we said the doping is non-uniform. So n is a function of x. So n is changing, right? This doping density, you have more n here, less n here. So this n is changing along the x. So let's say n is a function of x. And then in this equation, what is a function of x? Nc is a physical constant, okay? And the Kt, thermal energy constant, EF, as we said, is flat in this equilibrium state. So EC is changing with x, because here you have a slope. So this EC actually is a function of x. So let's take the derivative respect to the x on both sides. So then on the left side, you have dn over dx. On the right-hand side, if you take the derivative, because this term is inside the exponential function, then you take the derivative of exponential function. After you do that, it's still exponential function, but those coefficients, like over kt and the negative sign, should be pulled out in front of the exponential. So that's why you have this kt and the negative sign in front of the exponential. And then you can have the dEc over dx. Still you have the exponential here. This is the chain rule in the calculus. So you have, if you want to recall your calculus. And then you can notice that what you have here is the same as before. It's n actually. This one is actually the n. So you can replace the whole term here in this box with n. It's the same as before. So then you have this, n over kt, then dEc over dx. And this dEc over dx, what is that? That is a slope, right? Slope of this band edge. So as we said, the slope is the electric field. This is from the previous slide. This field is the slope, but you need to have a cube there. From here you have the cube, the charge. So that's why you have this. Okay, a little bit complicated, but eventually you get the dn over dx as this term. And let's write down this term here, this equation here. So you have this one. This is from the previous slide. The reason we want to derive this one is because we want to use the total net current equals to 0 at equilibrium. So this is the n-type semiconductor. We only consider the electron. So the Jn, you know, the drift and diffusion currents cancel each other. So this is a drift. This is diffusion. So they cancel each other. That means when you sum them up, it's 0. And then you plug in the dn over dx with this. Then you will get the following equation. And then you can cancel the common terms. This qn, qn. Then what is left is this mu n and q dn over kt. And after you rearrange, then it's dn equals to kt over q mu n. Or in other words, the diffusion constant is proportional to the mobility, and then the coefficient is the thermal voltage, because this kT is the thermal energy, and then Q is the charge. So thermal energy, as we discussed before, is 0.026 electron volts at room temperature, and then you divide by Q, that means 0.026 volts at room temperature. So this is the thermal voltage. And similarly, you can derive this dP with mu p is the same derivation. So here, this is a relationship between the diffusion and the drift, and this is known as the Einstein relationship. So this is the same Einstein, you know, the famous one. So this is just one of his minor contribution, and he discovered this in the semiconductor. So this is named after Einstein. Any questions? All right. So here let's for a summary here. I know this derivation is a little bit tedious, but you will have a similar problem in your homework too regarding this. But the key here is without external electrical field, the total net current should be 0. Internally, you have non-uniform doping, therefore you have the diffusion. But you have this built-in electric field to compensate the diffusion, where you have the drift currents. So the diffusion and drift should cancel each other, and then we use the total current equation equals to 0 to derive the relationship. The only thing here we want to derive is dN over dx, and this is the, let's say, the gradient or slope of the electron density along the x direction. So to derive this one, you need to go back to here, starting from the original equation for the electron density. But consider that this is a function along the x. Then you can get this dN over dx related to the electric field. All right. Then let's look at one simple example. So here, what is the Hall diffusion constant if the mu p is this number? So it's just a simple practice. You plug in the numbers, the dp, kT over q mu p, and this kT over q, as we discussed, is 26 millivolts at the room temperature. So you plug in the numbers, then you get this one is 11 centimeters square per second. All right, any questions? If no more questions, we can stop here today. And just a reminder, your homework 1 is due tomorrow, Friday, before the midnight. Please upload to the Canvas. All right, we can end today's lecture. Thank you.